Okay. Hello, everybody. We are now starting the first paper and talk session for this conference. The topic of this session is about web audio creativity and influence. And the first presentation is from Otto Rottier, coming from Utrecht, Netherlands. He is data engineer at Rijksoverheid. And he works with Benjamin Matuszewski, working at IRCAM SMTS, Sorbonne Université, Paris. So it's for you now.
All right, thank you. I'm very happy to be here. As mentioned, I don't really have a background in audio, nor academic, nor industry, but I do have a background in physics, so I might. It's very helpful in audio processing. And the company you mentioned is actually the Dutch government, Rijksoverheid, where I do non-audio stuff. But Benjamin and I did some work together, and our talk is called A Rust Implementation of the Web Audio API. And maybe the subtitle is even more important, Decoupling the Web Audio API from the web. And I hope in this talk we'll explain a bit how we're going to make this pie slightly better that Hongchan mentioned by moving away from the web. So first, let's assess what the web in the Web Audio API means. It's available in the web browsers, obviously, all three of them. You interact with it with JavaScript, and of course, you get full access to the browser's DOM, the audio elements, the media elements, basically the whole user interface. And then there's this neighboring APIs, such as WebRTC, media devices, media recorder, that you can leverage with the Web Audio API. But mostly, the Web Audio API is just an audio processing engine. It's an audio graph. It's well documented, easy to use, and extensible. And it enjoys some popularity. There's a conference going on, and we're all here. And our point is that the coupling to the web is not extremely tight in the Web Audio API. So why don't we just build an implementation from scratch with no web involved? That's great. A bit of reverb. I like it. So that's what we set out to do. And then the ultimate goal is to open up for new platform and application areas. I'm going to show two demos, which are command line tools actually running Web Audio API. But you can use it for desktop games, embedded hardware, or just tiny hardware where you don't want to involve the whole browser. And you can do scene pre-rendering, basically everything the offline audio context gives you without a browser. And then we widen the community outside of JavaScript. So our journey begins. We've read the specification really well. It's over 200 pages. It's quite a nice spec. It's the first spec I read. And we looked at some prior art, most notably the Lab Sound project. It's a C++ implementation that was forked from the original WebKit implementation, but it has since deviated from the spec. Still interesting to look at still. And then there are some academic exercises in pure JavaScript and Python experiments. And well, for fun and giggles, we decided why not build it from scratch. Of course, we could have also ported the existing browser implementations, but it's less fun. So if one of the first commits is in January 2021, where I'm scaffolding the audio context, which is quite important, as you know. And then let's have a look at the end result. This is a snippet of Rust code. And it should look really familiar to you. There's some import statements, you can forget about it, but basically we're setting up an audio context, and then we're setting up the audio graph. There will be an oscillator with a frequency of 400 Hertz. We ramp it up in volume and tween it back down. And then there's actually a cycle in the audio graph for a feedback effect. So this is Rust code. I'm going to run it now in my terminal, and it's interacting with the Web Audio API. It does look a tiny bit different from your JavaScript code, but there should be no surprises. Let me try this out. It should be right here. So here's the file again in my terminal, and I'm going to run it to show you that this is not just an academic exercise, it actually works. So this is the 400 Hertz tone with an infinite feedback cycle. Well, it's not too spectacular, but I hope you do realize it's the web audio API running outside of the browser. So why did we choose the Rust language? Because we want to jump onto the hype, of course. But actually, it's a language that is living up to the hype. It's a system language, much like C++. It's very low level. There's manual memory control. You can avoid garbage collection. And it brings the unique concept of data ownership to ensure at compile time memory safety, thread safety. There's no runtime overhead in the language. So we're fighting the compiler regularly, but it does ensure a smooth operation at runtime. And also it's very friendly for foreign function interfaces, so we can bind our core implementation back to other languages, and I'm going to show an example of this later. So the appeal was that it's very similar to C++, the king of audio processing languages, but it's not as daunting. It's a smaller language. It's very beginner friendly, has mature tooling, adding packages or dependencies very simple. And over the past few years, the ecosystem is really maturing to do cross-platform, high-performance audio I/O. It's very simple in Rust. The decoding libraries are maturing. So this was the right moment to start. This is a small overview of the architecture of the library. This should be no surprise if you've ever built an audio processing library. There's the notion of the control thread and the render thread. And the render thread has the sole purpose of shipping samples in time to the hardware to not cause any hiccups. So the audio graph where the nodes live topologically sorted, they're all in a render thread, and there's a callback which is running every millisecond or so to ship 128 samples to the hardware. And we, the community, we write our user space application with all the nodes and the contacts, and that is on the control thread or the UI thread, as you may know it. So what's the current state of our implementation? Most of the spec is implemented. There's a few nodes missing, but I think of the API service, we've implemented the big majority. As you saw from the code snippet, we did have to make some concessions to adapt to the Rust code style. And also Rust can be inherently multi-threaded as opposed to JavaScript in the browser. So we had to make it thread safe. And another hurdle was that there's no object-oriented concepts in Rust. So we had to introduce getters and setters for some stuff. Method overloading is a bit different, and we're using composition instead of inheritance. So there might be slight differences, but we've put a lot of effort to make it look like JavaScript code. So for us, the easy parts in implementing was the control UI thread, audio graph traversal and rendering. You need to sort the nodes to make sure they render in the right ordering. To do cross-platform high-performance I/O, implementing the nodes. There's 3 left. I'll mention them later. Sample accurate timings. And a nice thing about Rust is that there's no concept of acquiring the content necessarily. This is a part of the spec where you ensure unique ownership over audio buffers when you start rendering them. But Rust at compile time will verify this for us. It's really easy. The hard part is, of course, when the specification is hitting the boundary. So it's going to interact with DOM elements or neighboring APIs. And we need to come up with some simple shim to deal with it. For example, the media stream. We had long talks about how to compact it to the core thing that a media stream is, because there's no such thing as a native media stream in Rust. Then, of course, there's promises in JavaScript code. We need to map them to async primitives. It's not always hard, and there's a lot of work to do there. And the Web Audio API also has a lot of stuff around event handling, attaching handlers, and bubbling up. There's no native Rust translation for it, so there's work to be done. I just want to give also the example of the media element source node. It's a very simple node. You connect media into the graph, but there's so much behind it because a media element can communicate over the network or disk. It does buffering, seeking, reverse playback, pitching. We needed to implement a big chunk of all that. And of course, all the other audio stuff that is generally hard is also hard for us. Convolution in real time, anti-aliasing, head-related transfer functions, graphs in your audio graph. So I want to dive into the performance part. The render thread obviously has to keep up because we're emitting audio in real time. So we've taken special care not to use any locks, just atomic operations in the render thread. So there's no danger of priority inversion by the operating system. We generally try to avoid allocations and deallocations as they might take a lock on the global allocator and also lead to priority inversion. We're writing single instruction, multiple data-friendly processors, so you can use on a single core parallel execution. And we're preventing duplicate work if an audio stream is upmixed to an identical two-channel signal. The render quantum design is planar layout, float values, 128 of them, reference counted, so they allow for upmixing or splitting easily. And we're using an allocator that allows to reuse the buffers. Then the ugly parts, we've taken a look at the semi-official benchmarking suite of Paul, where we compare the Chrome, Firefox, and Rust version. What we're noticing is that we're being a bit slower, 3 to 6 times. So this is something that we need to divert our attention to. I think we can do a lot better. We've worked mostly on getting to feature completeness, but now it's time to look at the performance and also just steal from the existing implementations any tricks that lead to better performance. Then I will show a small demo that we've bind our library back to Node.js so that you can run JavaScript outside of the browser in the terminal. And the deal is that you then just write your audio code once and you can run it in the browser or in the command line tools. And officially, later we want to run the W3C test suite to check if our library actually does the right thing. It's written in Node.js. Show a small example of this. Again, it's a very simple demo. Here we see the JavaScript file or the Node.js file that sets up oscillators and it runs a callback every 100 milliseconds to set up a friendly tone. And this is running outside of the browser. This is command line Node. And as you can hear, great ensemble of tones. So yeah, so you don't need to learn Rust to use our implementation. You can just write JavaScript code. So not here, but maybe later in this conference, I can show you a bit more involved example where we're going to capture application sound, whether it's desktop gaming, a conference call, or a live stream, and then pipe it into our library and do transformations or recordings, room corrections, and then emit or record it. So we're really leveraging the power of desktop there. So just like Hong Chan shares his roadmap, I'll share mine. It's a bit less ambitious. But we're releasing the version 1 with the stable API soon. We need to work on 3 more nodes. 2 of them have a work in progress. And we need to look at performance and stuff I already mentioned. And of course, we're keeping up with exciting stuff in the web audio specifications such as variable render quantum size, performance heuristic, specifying the I/O devices. That's it. Thanks for listening. We're very welcome to contributors, users, and criticizers on this repository where we develop in the open. So thank you.
Thank you very much. Is there any question in the audience?
Yes, I have one from over here. Can you hear me? Yeah, we got a question. All right, my question is,
Wow. This is my live demo. I also do visual stuff. But I can hear you. Go ahead.
So you didn't mention this. What about working notes and specifically lesson working notes?
Sorry, I didn't hear the question.
in terms of implementation of nodes, that you can have some notes about workload node and some workload nodes.
Sorry, I didn't understand the question. Did you hear it? Oh, can you try it one more time? Sorry.
Try it once again. So there's a node called the workload node.
Ah, yes. Okay, I can expand on the workload node. So for now, we're exposing the internals of our library, which is called the audio processor API. And it's very similar to the audio worklet. It takes the inputs and the channels and it applies a transformation and it can be run stateful. So we are already extensible in a very similar to worklet node kind of interface. But it's not 100% similar to the spec. So we're actually keeping this option open, but in terms of performance, it's just generally better to use our exposed internal API for extensibility than to actually use the worklet node. But in any case, you can build a stateful self-built transformer that can cache data and can transform inputs and everything. So that is definitely possible in our API.
Hey, yeah, that is great to have a web audio API out of the browser. There are other web APIs that exist natively, and I think it's great that we could, once you taught or learn the web audio API, transpose this to native codes. It's great. It's a great proof of concept for the web audio API too. I think all is positive. Now, maybe I'm a little too old or something, but I'm kind of angry about this Rust thing. I don't understand that. And your justification seems odd. I would like to hear, in this community, there are a lot of great audio coders that can help us to get this done, or it's the easiest way that you can reuse your JavaScript code you wrote in the web browser. It's the easiest way that we can get fancy features around which are important communities, like the WebAssembly code inside the audio worker thread. That are very important arguments for the choice of the language and the environment you're coding this in, and they seem to miss. But maybe you can.
So the question is basically, why not C++?
No, this is not what I said.
Well, I think it's a fair question, and it also really has an impact on the type of contributors and the growth of the library that we can expect over time. So I'll be honest, I just like Rust. So this is also my learning experience. But to give a bit more broader argument, I have a gut feeling that the current web developers are more inclined, when they want to do system level programming, to move to Rust instead of C++. So I'm hoping to bring in a web developer community to our library, because Rust, it just looks a bit friendlier and nicer, and package management looks like the NPM package management. So I'm just hoping that these web developers transition to a systems language and they're scared of C++ like I am, and then they write Rust code.
Just a quick question, it will be the last one, I think. Did you reuse any of the Rust implementation from Firefox?
There's, interestingly, this artifact indeed, that there's a half-finished Rust implementation of the Web Audio API. We looked at it, but not heavily, but I think it will be a source of inspiration when we're going to optimize nodes further. Yes, it's a very nice relic that is now on the internet, the Rust implementation.
Oh, thanks. Hi. So Rust does have this multi-threading capability that you said wasn't in the original Web Audio API, but I think that could be very interesting in terms of new applications. Are you planning to develop in that direction?
Yeah, but I have to mention that the render thread is always single-threaded, so there's no movement there. So what we did is make the control thread thread safe. And I'm wondering if that is very interesting. It means that you can ship your oscillator node handle to one thread and your audio context somewhere else, but it's all control side, UI side stuff. So there's not a lot of performance gain there because the control thread hiccup doesn't matter too much.
Yeah, I just had a question about web UI libraries written in Rust. So I know that there's kind of a vibrant ecosystem to sort of try to bring all web development in Rust, so it composed to WASM. And then with these small bindings, have you found that there's a compounding effect? Like say that you're doing your web audio Rust, then in for a penny, in for a pound. So why not do the UI and the graphics and kind of, is there a compounding effect, or is it just sort of the opposite, that it's like adds headache on top of headache?
Yeah, I think we're going really in circles at that point, because you can build, of course, your UI in Rust, but to bring in my library to emit audio inside the web browser, that's just layers on layers, because then you'd use my library to render into a worklet processor to do the actual browser outputs. So I think we're going in the wrong direction there. I'm more inclined to invite you to use my library, and then maybe the port of the web, how is it called, the video card API that allows really raw visual stuff. It's also being ported from the web to Rust, and you can build like an optimized browser without a browser that is doing visual and audio stuff. So I'm more looking into that direction.